Welcome to the 1 week online STTP program on electric vehicle challenges and opportunities. Welcome to session 1 of day 4. Today we have again Dr. Alok Mani Tripathi sir with us, who is working in the field of material development and diagnostics of energy storage devices like batteries and supercapacitors. Sir is trained in energy, science and engineering from IIT Bombay. Presently, he is working in the Center of Material Science and Nanotechnology, University of Oslo, Norway. He work at various national universities in USA, UK, Taiwan, and in India at IIT Kanpur at various positions. Sir has many publications in reputed journals, and as we got to know that battery is the heart of electric vehicle, and Sir has very good research insights and research work related to battery of the electric vehicles. So I hope all the participants will get benefited by the lecture of Sirs again. So thank you so much, sir, for coming. I welcome you and I welcome all the participants. Over to you, sir.
Yeah, thanks, Professor Niti, for a nice introduction and very kind to provide this platform to interact with the CERT group and associated people with the CERT. So, good morning, everybody. And I just like to start my talk. Today it will be a bit longer than previous talk because today I'm going to talk on the battery technology, its safety and the management. So I will cover the topics about when the battery was discovered, what is the battery and used in electric vehicles, then the working mechanism of the batteries, safety issues related to the battery, then the generation of the batteries, how many generations are there and which generation we stand now, then battery manufacturing, how it was made, then how we are doing the cell assembly, then how the battery get failed during operation, what are the risk challenges and what precautions you have to take, then battery safety management, and then some suggested reading if someone wants to go further with the safety and standard testing procedures, and then summary. Basically, if you see the battery is not a very new device like electric vehicle. So electric vehicle, like people are thinking that the first IC engine has came, whatever present time we are using the car, but it's not the true. The first drive vehicle was the electric vehicle, and which has came with the discovery of this Volta pile. So it was discovered in 1800 century, and the electric car has came around 1836, and then it dominates the market up to 1890. So there was a time when electric vehicle was there, but when combustion engine has came, then it over dominates the market. But what happened with the time that the combustion engine has certain drawbacks. It starts polluting environment and then efficiency limitations. So people have think, okay, let's go back and be sustainable. And for being sustainability, they are going back to the same place and started for the electric vehicle. So this is the old technology in the new formulation, because the battery used in past time was very low power, but now it's a very high power. So Volta is considered to be the inventor of modern batteries, and some places you will find it is quoted that the first battery was made by Volta, which is shown in this picture, where the zinc and copper plates were arranged with one brine solution as a separator and electrolyte. So this cell was first designed, still it is kept in museum in Italy. But recently, in during excavation in 90s, in 2000 decade, so they have found in Iraq near to the Baghdad, around 30 kilometers away, in 1938. Sorry, this is a mistake, not the 38. It's a 95. So they find a battery, and here is the real picture. So it's like an earthen pot and then laminated inside. Then they have the cathode and anode, which is made up of iron and copper. So this battery is around 2000 years old. But why this battery was used? during Parthian periods, almost time of the Alexander. So why this was used, not yet known. But this was now considered as the first battery. Now, if we see the development with the era, so the one first battery device designed by the Volta, it has potential around 1.1 volt. Then further it was improved by Ritter, and then it is going to be 1 volt with the different chemistry. But the main thing will come with the rechargeable battery, because this was the primary battery the Volta has designed. Then we have a rechargeable battery, like lead acid battery has came. Rechargeable means you can discharge and again charge the battery and reuse. And primary battery is once you use and you have to throw it. So then lead acid battery has came in 1854, which is still existing. So it's one of the battery which has spent longest time into the market. Then we have the zinc manganese 1.4 volt with primary. Then we have the nickel cadmium. This has came in 1980. So this is still in use with much higher potential. And the same way aqueous ion battery system has came, then lithium metal system has came in 90s. But very conspicuous thing is that after 1990, this growth of battery market is very fast, especially with regard to the potential. Because when lithium has came into the picture, it suppresses all kind of battery technology. Why? Just because it has a very high potential in compared to the other technology, which is lying just near to the 2 or below to the 2. But lithium starts from 3 onward. So in present time, we can see we are in the range of 4 to 5 volt. So this potential depends. I will explain in next slides how this potential depends. And then after that, we have some others technology also, which is still in the research, where we can increase the capacity while compromising some amount of the battery potential. So if we see over here, the competition is now between different kind of battery technologies. So I have shown in previous slide like lead acid battery, nickel cadmium, metal hydride, lithium ion, then future lithium means the advanced modification in the battery materials, and then zinc air batteries, lithium sulfur and lithium air battery. So what is the governing factor for this? So it's basically what we are looking in the battery is about the specific energy, and specific energy is directly related to the voltage and the cell capacity. So if we plot different kind of energy system with specific energy, then how many kilometers one battery can go? So if we take the lead acid battery, we can see we can go with only 50 kilometers with the car. Then if you have a nickel cadmium, we can go 80 kilometers. Nickel metal hydride, we can go 100 kilometers. And with lithium ion battery, we can go 160 kilometer. Future lithium ion, since this reference is from an old publication, so now the battery field is modifying very fast. So this future lithium is still in commercialized state in Tesla. So this is the high potential 4 to 5 volt batteries, and they can go more than 350 kilometers in one charge. Then we have an air battery. These are under research. So these are future possibilities. Why? Because we can go higher kilometers in one charge. So here one example was given with the Nissan Leaf, and this 200 and more kilometers which is going is from the Tesla. So they are using this battery in their system. And if we see about the air battery, so this looks very, very, very challenging and very, very sustainable to the in making the electric vehicle very, very much more feasible. So how we can compare this thing? Again, we have to look about the specific energy. So here there is a plot, a bar diagram, which is showing the specific energy versus different cell chemistries. So if we see the lithium air battery, it's not the ion battery, it's an air battery. So if we take the lithium air battery, its specific energy is very, very high, very promising technology. And then working potential is around 3.5 volt. If you see the lithium ion battery in the last of this column, it has very high potential in present time, going around, working around between the 4 to 4.5, depending on the what kind of chemistry was used inside the cell. But it has a very low capacity because specific energy. So what is happening? We have less energy in the pack, whatever we are putting into the battery system. So air definitely has plus point, but it has lots of technological challenges, research challenges, which still need to find out. Second to that one is aluminum air battery, because it operates at around 2.7 volt, and then it has specific energy second to the lithium. So now people are looking for, as a possibility to this one also as a second option. Why this aluminum is looked as a second option? Because lithium, first thing, is not universally available in the world, and cost of lithium is bit higher, not is a bit higher than the aluminum. And benefit with the aluminum is that it is available everywhere. Cosmopolitan things are there, and then the earth crust availability is also more. So like one Indian company, here I have added one news article. So one Indian company, Log9, they have claimed they can go up to the 1,000 kilometers with just one recharge, one charge in the battery. And one research paper has shown the application of this aluminum air battery into the small electronics devices. Like I have told you, classification of the battery electrics. So in small electrics also you can use. One example is given here in the hand watch. This wrist is assembled with the aluminum batteries, aluminum air battery. So in this battery, in this way, they are showing the practicality. But what is the limitation in this one? This, they are going with the 1,000 kilometer, but you don't have the option to recharge. So the Log9, which is claiming, they are claiming for basically you can say the mechanical recharge. As I in my previous talk I told you, there are two kind of recharge in the batteries. One is the electrical, another is the mechanical. So they are considering as a mechanical recharge, and it still has the challenge. So they are in the testing mode. Still they are in the testing mode, not yet commercialized, but possibilities are there with the aluminum. Then we have a magnesium air battery, which is again challenging, but it has lots of problems, magnesium, and operating potential is not as per the theoretical. It's losing half of the potential during operation. Then we have a lithium sulfur. So after the air battery, lithium air or aluminum air, this lithium sulfur is the second most challenging technology, and the possibilities are there that after the lithium ion battery, this lithium sulfur will be the successful in the electric vehicle. Why? Because it is again almost triple of the specific energy than that of the pure lithium ion battery. So, and they are not going very far away from the lithium ion chemistry. So the chemistry is almost same, just some problems are existing with the lithium reaction with the sulfur. So if that can be sorted out, it could be a better alternative. So they are very near to get in electric vehicle, and some companies are doing trial also, as I know. But air batteries are far away from those. So if we see the working mechanism, how these batteries work. So basically you see, I emphasize 3 batteries. So I'll explain here about the 3 batteries because we are discussing about the lithium electric vehicle. So electric vehicle particularly feasible with these 3 options in present time. In future, maybe some other technologies come. So first you see the basic lithium ion battery, how it works. So basically this is called the rocking chair battery. Why? Because as the rocking chair swings when you sit on that, same way, this battery also moves the lithium ion between the cathode and anode. So cathode and anode has the proper space in their lattices, in crystal lattices, and then they can accommodate during charge and release during the discharge of the cell. In between, there is a medium called the electrolyte, and it has a physical barrier to avoid the short circuit between the positive and negative electrode, and that's called the separator. Usually separator holds the electrolyte in some microliters. And then here you can see some structures are coming. This is coming with the reaction of electrolyte with the electrodes, and that's called the interfacial layer. So in general, for this example, as I have shown, the chemistry is going like this. Lithium, when graphite has the lithiated stage, so it has the lithium, it releases the lithium going to the lithium cobalt oxide lattices over here, and then carbon is free, and then lithium cobalt oxide is formed. So this is the way which a basic lithium ion battery works. So it's not only one example of lithium cobalt oxide, there are multiple examples out there. This is the first generation battery of the lithium ion battery, lithium ion based system. What is happening in the air system? We are keeping lithium as an anode, not the carbon. So we are using pure metal. So reason for using the pure metal is that we are trying to utilize the highest potential of lithium in without addition of anything extra things, and this is the lightest than the any other element like carbon or non-gaseous elements. So in lithium air battery, what is happening? We can use metal as a anode. Then we have an electrolyte. Then we have a separator like in the ion battery, and then we have modification on the cathode side. So here we have a some porous membrane which can use oxygen as a cathode, because in this battery oxygen is always acting as a cathode, and this is a gaseous oxygen. So in gaseous oxygen, these oxygens come to this surface, porous surface. This is loaded with certain catalysts which break down the, actually reduces the oxygen, and then oxygen reacts to the lithium and form the lithium oxide. So depending on the electrolyte which you used in this chamber, either it is non-aqueous or aqueous, it is forming the product like lithium oxide and lithium hydroxide. Same mechanism follows into the aluminum ion battery, aluminum air battery, not the ions. Aluminum react with the oxygen with water and form aluminum hydroxide, and then it going back during the discharge. So this is the basic function of this battery. So you see what benefit you are getting. Like in the lithium ion battery, you have a physical electrode. Here you have a gaseous electrode. So because of the gaseous electrode, you are able to save the weight of the battery. Because if weight will increase, definitely your energy density will go down, because it's watt-hour per kg. And the chemistry is also giving some enhancement into the capacity. That's why overall density, energy density of the air battery is going up. Next alternate is sulfur battery. As I told in my previous slide, the lithium sulfur battery is very much close to the lithium ion battery, because just replacement is that in this one we are using the pure lithium metal as anode. Some alternates are also coming into the, but it's not in the market actually now, but the whatever sulfur battery coming in market with the pure lithium metal. And another side we have a cathode, which is a composite of sulfur and carbon. And then we modify a little bit electrolyte in compared to the lithium ion battery, and this electrolyte allows the lithium sulfur battery. So one interesting thing I like to tell you, when the lithium ion battery first discovered, it was again the sulfur based chemistry, because the cathode was used as the titanium sulfide, and but because of the low potential it was discarded, and then this cobalt based system has came, and finally this become the champion in the battery market. So with sulfur battery, the lithium is reacting with the sulfur, forming the Li2S. But the problem with this battery is there are lots of other polysulfides are forming, which is a drawback. Lots of things are coming in the research, which is improving the performance of these batteries. But because of the capacity and specific energy density, this is a preferred thing in compared to the conventional lithium-ion battery. So if we see two major important parts, here I will little bit describe about the material chemistry. I tried to avoid the most of the material part in this talk, considering the audience. So here very little thing I want to explain about the present generation of the uh, material used in cathode and anode, because these two terminals of the battery decides the overall cell potential and the capacity. Although electrolyte is also an important part, but the role in deciding the physical property of the cell is through the cathode and anode. So here I have shown some crystal structure. Basically, these circular atoms are the circular things are the atoms in different colors. So this is showing a different kind of atom in their unit cell or crystal lattice. So here is the example of lithium cobalt oxide. So where the lithium lies in between the cobalt oxide channels. Then cobalt was replaced by some manganese and nickel in 2008. And then further, what impact we got out of this? The lithium cobalt system has the problem that in first cycle itself, we are losing 50% of the cobalt from the lattice. So I'll not go in detail how it is happening, but they have used the nickel manganese with the cobalt, and finally the system got stabilized. And with that, since they have used the nickel, so the potential has gone up. And when potential has gone up, so their capacity has increased. And then they have replaced, then they have several compositions of this one, nickel manganese. Even present time, the Tesla is using the same composition, which has the best batteries, and I have shown in my previous talk. So they are using this composition in 811 form. Then we have another thing is that to make this lattice super rich with the lithium. So if you make more lithium, which can move into the system, then it could have more higher capacity. So the capacity can go up to the 270 milliamps hour per gram with the existing cathode. Similar way, if we see the anode side, because both are very important, because one is releasing the lithium, another is accepting the lithium. So anode, conventionally, when the battery has came with the reversible battery, it has used the graphite. Why graphite? Because graphite has the layers of graphene, and that layers can include the lithium ion inside that. When it includes the lithium ion, there is a very minimal volume expansion, less than 10%, and then it releases when it is needed. And second benefit was that it is almost near to the lithium intercalation potential. It's very near to the lithium reduction potential. So we have some alternate options also, because graphite has the rate limitations, and then temperature dependence is very high. Then side reactions are very high. So because of those things, people start looking for the other materials also. And the basic difference between these two anode material are, one, the graphite one is based on the intercalation, because the ions go into the layers of atoms and get intercalate, while other two reactions are, they are doing direct electrochemical reactions with those metals or non-metals, and then when they react, they will go in different phase. If they go in different phase, so definitely they increase the lattice size. If lattice size increase, then overall material starts breathing. Breathing means expansion, like our lungs are expanding during when we take the breathe in. So one is the alloying reactions, where lithium form the alloys with the metal used and expand. Then we have a conversion reaction, where lithium don't alloy with the metal, but react with counterpart of that and then convert back. So in anode, we have three technologies. In cathode, we have multiple, but here I explain the two technologies, layered and spinel based material. And both has a plus and minus. All materials has the plus and minus. So if we see about the generation of batteries, this is very important because the research is following this trend. So in first generation of the battery, cathode was LFP, lithium iron phosphate, or this NCA cathode, and anode was 100% carbon. Okay, so then generation second has came for the batteries. This has the NCM, nickel, cobalt, and manganese 111 system with 100% carbon anode. Then second generation has came, where the other composition of nickel, cobalt, manganese oxide based system were used with the different compositions 5, 2, and 3, and then 6, 2, 2 ratios. Now we are in this stage, generation 2. Generation 3 has just started. Still, there is no news where they are using on sites, but soon, it's very soon, maybe in 1 or 2 years, they will start using this one. So we are at the present time at this stage, generation 3. So what we are using, basically we are using either 622 NMC, nickel cobalt manganese paste, or 811 composition. And in anode, what we are doing, we are using little bit of the silicon with the graphite. So it's going to be the combination of intercalation with alloying in the anode side. So why it was doing? Because we want to minimize the drawbacks of carbon by compromising less into the specific energy side. Then next generation 3 we will come, where we will have a very high voltage spinels and anode will be mostly governed by the silicon, less in the carbon. And then generation 4, which I explained, is about the other alternate chemistries of the lithium, which is lithium sulfur battery, and generation 5 is the lithium air battery. So the probability is that all will come in next decades. 20 is going on, battery development is very fast. So it is possible that these generation 1 and generation 2 lithium cell is still in use. It is in market and used in everything, small electronics, vehicles, and the medical devices. Everywhere this is used. These cells are under optimization condition, generation 3. Generation 4, 5 is also under optimization, but it need more research. In these two, sulfur is more closer in compared to the air. Now, how battery is made? That's another question. So I have explained about the material. Now, how these materials are made. So I'm not going to the chemistry, just very simplified flow diagram of this. So first, basically, we take the carbon. So carbon is used in the form of graphite because graphite is has the layered structure. We can't use the diamond. Diamond is also a carbon. We can't use a coal because of the two reasons. Because the graphite gives the sp2 structures and it has better conductivity, electrical conductivity, in compared to the other two form of the carbon, and it has the interlayer spacing, so which facilitates the lithium intercalation. So basically what we do, we can synthesize this thing, graphite, into the lab, otherwise we can get it from the ore and purify it. So in first step, when we have to synthesize, we are using some carbon precursors, then calcination means heating, then we are crushing it, grinding, and then classifying. Then it was carbonized at very high temperature, and then we process it to use. Same way in mining, when we are extracting the graphite, we are purifying it with different chemical processes and finally making it ready for the electrode. If you see about the other two alternatives of the anode, using the pure metal as I shown in the sulfur battery, or the silicon as a pure or the alternate, so we can do the synthesis of the silicon in the lab. Otherwise, it's directly available in the earth crust also, but not a single company who is directly using from the earth crust. Everyone is doing the synthesis, all the big companies in the world. So what they are doing in this one, they are doing the plasma based gas phase synthesis, and they are using some organometallic precursors, and then they are precipitating in the form of silicon, some amount of the silicon oxide as a composite because it is utilizing the cell, or pure silicon oxide is also in use. So they are mixing, carbonizing, and then milling. Sometimes they are using the carbonization to just improve the performance, is coating with the silicon particles, and sometimes they are coating with the silicon oxide also to increase the performance. So it can be used like that. Then lithium metal, directly we can use, we can clean it and then thin it, and after thinning, thin rolls can be used as an anode. If we go to the cathode side, again we have to synthesize those materials, and synthesis at the bulk stage is still a challenge. All materials which are known in a small scale, it's not compulsory that they can be synthesized into the bulk scale, like in kilogram or 2 kilogram, because of the lots of impurities will come which can create a problem in the cell. So the co-precipitation method, which is a commonly used industrial method to make cathode material. So they used to take the precursor, precipitate, and then calcine the things. And after calcination, they remove the impurities, means the other products, and then finally they get the your desired particle, and then they are tuning something into the chemistry. I'm not going into that. So they are modifying something into that so that they can tune the particle size, because this also affects the diffusivity and lots of kinetic parameters are getting affected. Even the internal cell resistance is also getting affected by the particle size. So these are very important things. So they are doing lots of modifications to get better particle size. Sometimes they are doing the surface modifications also, like doing some kind of metallic coatings. And after that, the lithium phosphates is also has some method to synthesized, and these two kind of cathodes are there based on oxide and the phosphates, because phosphates are more stable and more safe in compared to the oxides. So these two are the methods to make the cathode. And then the important part is the electrolyte, because these allows ion to transfer between the cathode and anode. So with this one, they are using lots of synthesis method, because we don't have we can't use water as an electrolyte in this one, because water, if we take the water, it will decompose at very low potential, so we will not able to extract all the benefit of reduction potential of the lithium ion. So basically we are using the organic carbonates. So these organic carbonates, like ethylene carbonate, the structure was shown in the bottom over here, ethylene carbonate. So this has the carbonate group COO attached with some organic group, and it is ethylene group, so it is called ethylene carbonate. So like we have a propylene carbonate, diethylene carbonate, lots of variants of this are available, but upper terminal remains same. This specifically has some chemistry because of which we are using it. I will not go into the detail. Then we are using some salt into this electrolyte, and those salts are LiPF6, which is most commonly used. Some chlorates, LiClO4 is also used, but most preferred is lithium fluorophosphate. And the synthesis was through the lithium fluoride and the phosphorus pentachloride. And these electrolyte contains around 0 to 10% weight of some external additive, except to the salt and solvent. 80% of this composition is from the solvent. 12% is from the salt, which is a lithium ion carrier. And then 0 to 10% we are adding certain additives for battery management basically. And those additives sometimes works at the interface also. So there are several classes of additives, but their concentration is very less. Then third part, where we load our electrolyte into the cell, is the separator. So separator is always a polymer. So in polymer, they are using either the cellulosic based or the plastic based. So we are using a conventional polymer technology tool. It's a melt extrusion technique, where they are melting the polymers and it's coming to the through a roller, and then we are getting the sheet. After getting the sheet, they are doing the length orientation, transverse orientation, then thermal settling. Why they are doing all these things? To maintain a proper pore size, because that is again very important factor in deciding the performance of the battery. And then they are doing the winding and then slitting of the separator and using into the, finally they are doing assembly of all the components, cathode, anode, separator and electrolyte. This assembly is going on, and then finally the cell is getting sealed so that it should not come into the external environment. These processes of assembly and the lamination going into the inert chamber. It's not into the oxygen and water atmosphere, because the lithium is very reactive with the environment which has the moisture, and it can catch the fire. When they do the cell assembly, how it looks. So as per the need, present time they are doing different kind of assemblies. So here you can see the example of ever ready battery, although it's not the lithium ion battery. I have taken this picture just for the example so that people can understand in an easy way. So this is a cylindrical cell. In technically it is called 18650 cell. And in this cell, if you take in lithium ion battery, 3.8 volt, 1.5 ampere hour cell. So in this cell, you can see you have a cell can, the external body. You can see here in the real picture, external body, which can be a polymeric things or in a metallic cap. Then we have a lamination of current collector, like copper and aluminum are there. These are the current collector for cathode and anode. Then we have a carbon material on top of that. Then we have a separator, which is soaked in the electrolyte, and finally it is assembled and rolled in a form, and then electrical connection was given on the top, which you can see over here, and another uh, terminal was connected on the bottom, so you are getting the cell connections over there. So this will have a much higher capacity, means the packed energy density. In coin cell, for smaller applications like in electronics or in our watches or in some toys, you can use this small system, circular cell, and these circular cells are called the coin cell, and this is also technically called the CR2032 because of their dimension, basically. So this is technical code which we used to have in we are using in our research and other purposes, but commonly it's called the coin cell. Then we have another assembly in the pouch cell form, and then prismatic cell. This is basically called prismatic cell. So here the rolling of the same components, all the cathode, anode, current collectors, and electrolyte, and then cans, is in the prism form, means you can say the rectangular form. And here is the example of one Nokia battery, where the internal are shown over here. And same way we can change the electrolyte with the plastic electrolyte. This is called the plastic battery. Actually, this is more stable in compared to the lithium ion battery, just because of the electrolyte is very safe in this one. So these are 4 major assembly nowadays used for batteries after making electrode. One more example I want to show from here is the thin film batteries. So this is again the same coin cell kind of, and it is used mostly in the electronic market. So here I have shown one of my research where the carbon and binders are the essential component in all other part, but you can directly make your cathode and anode deposited on the current collector without using any carbon, any binder. So you can minimize your weight inside the battery so that you can increase the energy density of the cell, and then you can get a very good performance, rate performance. So for this one, you can see the electronic things where we have a very little space. This kind of battery can be very useful because this will have more energy and less space. So here we have tested for this battery. Actually, this is a half cell testing, not the full one. But you can see as we are increasing the current of charge and discharge, the capacity is going down. So in my last talk, someone has asked about the reducing the charging time. So here I like to answer, if you increase the current, so what is happening? It will push more of the electrons into the system, but material is not ready to take. So what it will do, it will compromise with the capacity. So if you go for more faster charging, you will start losing the capacity. Means you will store less of the energy, and more of the current you are putting into the cell, it will just go into the heating. Now, what problem battery is facing? So you just see the news articles. So when the battery was came in market, from that time even till today, we are listening the news about the batteries and then safety related things. Why this is happening? Because the major problem is not with the lead acid battery, because the major problem is coming is the hydrogen evolution during the charging, but it's not very much complicated because the amount is very less. But when lithium has came, you have lots of benefit of using the very high potential and high capacity and energy density. But with that, some problem has came, like the reactivity of lithium with the water is very high. So like BL5C has came. BL5C, they have withdrawn this from the Nokia mobiles and then they replace it with that one. So what problem they have observed? They have some problem into the battery management system, means how they have assembled. Sometimes they have a problem with the lithium chemistry also. So like in BL5C, they have both problems, how they have assembled inside the mobile, and second problem they faced through the chemistry. Same way, Samsung Galaxy Note 7 has the problem. Then Lenovo laptop has the problem. So all the companies has to withdraw these products just because of the problem in the batteries. So battery designing, which I explained in my previous slide, this is very, very sophisticated process, and very smart hand are required to get proper performance out of the battery. And not only the battery, even where you are making the battery, that is also very important. So like here is the news about the New Delhi battery factory collapses in fire in New Delhi. So why this is happening? Because I told you this battery markets and battery components are very sensitive to the fire. So you have to take all the precautions. Once battery is back, the chances are very less. I will explain what are the chances once battery is getting damaged. So here I will give some example. What is the internal problems in the battery? Why battery get fail? So if you do the charge or discharge very fast rate, then that time what is happening? One example over here from the prismatic cell. So you see the when cell is very normal, it is very symmetric. When you discharge it very fast rate, it got swell. Why it is swelling? Because I have shown in some of my previous slide over here. You see the electrolyte component which we are using, it finally decomposes and generates some gases. Like here you can see the CO2, CO, carbon dioxide, monoxide, and some water is coming. Then there are some secondary reactions. Then these electrolyte again decompose into the ethane, ethylene gases. These are combustible gases. So these gases can create the problem. And because of this reason, this is swelling. So this is happening because of the internal reactions. Now the question will come, why we are using if they are generating the gas? Same thing happen when we increase the temperature of operation. So we can see the swelling, and then finally the cell is bursting because the internal pressure is going very high and it bursts. So again the question is that what is happening? So the thing is that you have to go a bit into the chemistry of this again, and more into the quantum mechanics of the battery design. So if you see the potential windows of electrolyte and electrodes, they are not matching, but we don't have any alternative also. So we are using this one. So what is the problem? The potential window of the electrolyte is less than the cathode and anode, and because of that this electrolyte component used to break. When it breaks, it forms certain kind of interface layer on the cathode and anode. Then in further cycle it stabilizes the cell. But if you change the dynamics outside, like you are trying to do the very fast charging and then increasing the temperature, this interface breaks. And if interface breaks, then again you are in the same regime to produce the gases inside the cell. So this is a very simplified example. It's a very complicated field to explain. Even still today, lots of things are not known, and so many things are known. So I'm telling some common points out of that. So what is the solution for these internet problems? So what we are doing, we are cutting the potential of the cell. So here is a typical example I have given of one cell discharge. So cell is charged to 4 volt and going to discharge at 0 containing 100%. So these three factors are very important: state of health, depth of discharge, and state of charge. These three are very important for the to sort out the internal problems of the cell, and sometimes external also. So what we are showing out of the state of health is, if you have some cell using into the drive, your electric drive. So with the number of cycles, how it is losing its total capacity. Like here it is shown 100%. In second cycle, you are getting the same 100% or you are going to get less. So like yesterday, I showed you about the Tesla. After going 3 lakhs of the kilometers, it loses around 50% of their initial capacity and retaining 85%. So that 85% is the state of health. Then depth of discharge and state of charge. So when you're discharging the cell, basically what we are doing, we are not discharging 100%. We are cutting to some potential. And this is a trick to use into the battery management system. And then state of charge, same thing we are doing. We are cutting the charging up to a certain point so that we can save the battery and enhance the battery lifetime, and we can minimize the failure of the battery. There are some external failure methodologies also there. Like if you are driving the car and car has the accident, then what kind of problem it may face. So like something got penetrated inside the battery over here. So if here it is giving with the example, not intentionally we are going to pin something inside the battery. It is an example, like something mechanically going in and penetrate the cell. So what it will do, it will definitely do the short circuit. And if it do the short circuit, so you know this internal resistance will create lots of heat, and then fire, gas, everything will be there because it will come in touch of the external environment. Same kind of crushing will be there. It will deform the cell. And then pinching means you are from pressing the cell from all the directions. Suppose if accident is very severe and then cell is completely got crushed, so it will be useless and it may burst. Then we may have the short circuit problem. If your assembly of the cell is not good into the system, like I have explained in previous laptop batteries in Lenovo, they have take back because they have this short circuit problem. Their space was very less and the cell was pressed. Then overcharge problem, if you're doing overcharging of the battery, again it's generating heat and it's a problem. So these two are basically the electrical problem into the battery, which is coming externally. And then we have a thermal losses, like if your battery is going to get exposed to the very high energy radiations, which can cause external heating or the environmental heat, like you are driving somewhere in the very high temperature. So this kind of problem may come. Otherwise, if your cell has some leakage and coming in contact with the water, then it can create a problem into the cell. So these four major categories which are externally impacting the battery. So how to minimize this one? Or what could be the consequences? So minimization, how to minimize this impact of mechanical, electrical, thermal, and chemical, I will explain in the next slide. But what will be the consequence if this happens? The consequences internally, if we see, it could have the internal short circuit, unwanted irreversible reactions, which we don't want. Just because of coming in the open oxygenic environment and water, it can give you different kind of reactions which is irreversible. Then flammable gases can come, and then fire in the electrode and the formation of dendrites. This is an internal problem. Then external impact can generate the heat, gas, fire, and thermal runaway. So basically, if you want to see how anything burns, so you have to go with the fire circle. So in fire circle, you need three things. One is the oxygen, another is the heat, and third is the combustible substrate, which can burn. So here, cathode is a supplier of oxygen. Even electrolyte is also giving some component of oxygen in later stage, in secondary reactions. Then anode and the electrolyte is completely flammable thing, because you have a carbon which can easily burn. And then environment means like heat is coming through the different sources. So here I have categorized the heat generation inside the cell, which can be a reversible or irreversible. So if you see the reversible cell, this is coming just because of the electrochemical reactions. But irreversible reactions, irreversible heat is coming from the ohmic resistance or the polarization in the cell, or some side reactions which is happening in exothermic in nature. So these reactions, these heat creates the gas, which you can see over here. This is a laboratory test performed in the Kolbach Institute in Germany. So the gas is filled and it's start coming out. And if it gets heat, it will make a fire like this and catches the fire. So this is the condition I'm explaining during accident, either internal or external. And this table summarizes everything. So like if you are going for the overcharge and external heat, so what it will do, it will instabilize the cathode anode. Then reaction with the electrolyte, it will generate heat, and these all will cause a thermal runaway. This term is called the thermal runaway. Means the temperature has increased, fire is there, this will cause thermal runaway. And if thermal runaway is there, then whole battery will stop working. These gases are again build up inside the pressure, then cell opening, rupturing, these kind of problems are there. Then external short circuit if happen, uncontrolled heat generation will be there. Then if it's some mechanical impact is there, deformation is there, it will cause internal short circuit. Then there are something coming from the inside the cell, like cell balance and converting. Lithium dendrite is coming. It will internally short circuit because it's an inherent reaction inside the cell if you don't manage the cell in a good way. Then depth of discharge is going very high, then copper dendrite may come. And then manufacturing defect if is there, like misalignment of the electrodes or the loading, cracking, so many things are there in this one. So separator get failed, and then what could happen? The cathode and anode can touch. So here one thing is missing, I will connect this one, because thermal runaway is also make cell fail just because our separator get melt. And when it get melt, directly cathode and anode positive and negative terminals touches and cell got stopped working. So the final consequence of these accidents are fire and smoke and the gas emission, which is not good for and no one wants into the batteries. There are some consequences also coming from the additive side. So we are using certain additives into the cell, which is a fluorine based additive, and we have a salt, as I showed you in the electrolyte, is also lithium LiPF6. So this fluorophosphate salt, sometime if some water or moisture is remaining into the cell packing side or it's going externally, it starts forming some harmful chemicals like hydrogen fluoride and all those. So here we can see the capacity is this one. But question will come. These are corrosive chemicals, no doubt, but released during the accident. So if it is happening during accident, and I have explained so many type of accidents, so the question will come, should we use this battery we should use or not? So for answering this question, we have to look about the energy released when you are burning your fuel, and you have to compare with the existing technology. So in existing technology, if we see with the diesel, crude oil or LPG or petrol based system, the amount of energy released after accident and catch the fire is 40 to 50 megajoule per kg. But with the battery, it's just 2.5 megajoule per kg. And in the battery itself, the most of the energy which is coming from the electrolyte. Least one is from the anode and cathode. So if we compare battery with reference to the accidental condition, the battery is much more safer in compared to the diesel petrol car accident or even the hydrogen based car accident, because it releases the very less energy. You will get the chance to escape out of your electric vehicle and you will be safe in compared to the diesel and petrol. Now how we can minimize these accidents and how we can effectively use the batteries. So for this purpose, we are doing basically battery management. So what is battery management? Whatever I have shown you, you have seen all the single cell results. Just one cell is there and all kind of accident was explained. So if it is a single cathode anode, this is called the cell, electrochemical cell. When you combine more than one, this is called the battery. When you combine this more than one, in the generally it's around 12 cells, then it is called the battery pack. And this kind of battery packs were used in the form of modules in the wherever you are using. So how to decide you have to use the battery pack or battery module? This depends on the application. So it depends on the environment, which environment you are going to implement, how many people are present there, what are the temperature over there, what are the humidity, external conditions. So many things are there, which is a point of consideration to make assembly of these batteries. Then battery size and type also matters. Like here I have shown the examples of the cylindrical cell, but you can use the pouch and prismatic also to make this kind of things depending on the application. And then design and implementation means how you are connecting the batteries, either it is in series or parallel, depending on what kind of current or potential you want to drain out of this. So accordingly you can arrange and give an electrical connection to this module and battery packs. Now one question is very important over here. If we have a pack, then why we are designing the module? So basically this is again I have explained these 4 points that has something to do with that. But another point is that suppose if your cell got failed, so you don't have to remove everything. You can just remove one pack. And now even nowadays some companies are thinking to remove individual cells also. So they are using certain kind of adhesive in between so that they can disassemble and then reconnect and replace and make it functional again, whole battery module. So this is again another technical things into the battery module design. So when we are doing this kind of thing, this has some benefit also and some loss also, because you see here the cost analysis. I have given. So pros is that it saves some space, because if you are using the individual battery, it will be scattered here and there, and then the electric drive, we are on the move, so it has lots of mechanical jerks, and that can disturb different things inside the cell, even the connections also. So it protects from all external shocks, heat, and then vibration, whatever your vehicle has, with the bumps in the road and all those. It makes the transportation very easy, handling, replacement, all those things become very easy if you do this kind of packing into the cell. Then minimize the installation cost. You have to go with the just 50 cells and 66 installation, not the each cell you are putting there, so it will cost more. So by making module, you are minimizing that charge also, and it's easy to connect the cell from each other. What are the losses with this? Is the increased cost, because you are using certain non-required thing. Non-required means electrochemically non-required thing. So this increases some cost, and definitely that material has the some weight, so it compromises with your energy density, and then assembly again has make some charges into that one, and then you have added one more layer, means if sometime your battery pack material may get failed. So that time you have a financial loss. But what is happening with the increase in technology, we can see over the financial aspects. So for cell, like in 2013, for per kilowatt hour, we are spending around 446 US dollars. And while for the pack design, we are using 204. So in my previous talk, I have shown you about the cell level capacity and cell level benchmark and the pack level. So this is I'm talking. This was the concept for that previous talk. So what is happening with the time? In 2013 to 2018, if we see, the prices has gone quite low. Means the ratio between the packing material and this is going down. So we are in the very positive direction, and hope so this will be very effective. And here we have a one Samsung SDI battery model, which they have launched in this year only. So you can see this. This is with the 18650 cell, cylindrical cell, 37 ampere hour battery and 94 ampere hour battery module. So this is again the part of the physical management. Basically, whatever I have shown in over here, these are coming to the physical management system. Now to improve further, we can categorize our management system, the safety management system, into levels: pack level and then cell level. Cell level, we can, if you see, we can do the cell design, and in the cell design we can do the electrode coatings, shutdown separators, safety vents we can use, and then safety circuits we can use inside. This is both by physical circuit and by the chemical circuit. We are adding some additives into the cell which terminates the cell at crossing that potential charge. Then positive thermal coefficient material we can use, which can easily liberate the heat generated inside the cell, and it will go outside to the cell packing, and then from there you can take it out. Then in cell chemistry, we can very smartly select the electrolyte, additives, and anode and cathode, so that we have very minimal amount of the heat generation inside the cell. Other way, if we see outside of the cell, which is called the pack level management, we can do with the electronics, and then thermal management. So we can do the all kind of active and passive management. Here I have shown one battery management system example, energy. So here the battery packs are there, and in between that they have implemented lots of sensors. And then we have a cooling system, air cooling system. So this both kind of cooling system can be used, air-based system or with some coolant which is circulating next to the battery, and it can extract the heat and minimize the temperature between the packs. Then we can avoid the short circuit, overcharge, over voltage, and thermal coefficient using the electronics, means having some program, smart battery management programs, and then with that one we can cut out this cell operation by compromising some of the energy we are not going to use, and some we will use. So with that one we can manage a better cell performance. So here is the example of the electronic part. So what we are doing basically in electronic part, we are measuring first thing the current and voltage of the cell, and third is the temperature. So temperature is both internal and external. This both can be measured. For external, they are using the sensors. For internal, you can use the impedance spectroscopy, where you can apply some frequency AC through the AC circuit, and it will give a relation with the temperature, how the internal resistance is building up, and then you can calculate it in an indirect way. Some research is still going on to use the internal sensors in the cell, but it's not feasible yet. People are doing research on that. So basically, with these parameters, they generate two kind of model. One electrical model they are generating, means directly knowing exact potential and current of the cell is not possible. So what they are doing, they are doing some modeling, keeping equivalent circuit of the cell, and then they are estimating, okay, the cell chemistry is going to perform in this way, and then they are correlating those these two models, and then this model was used with the all parameters for the battery charging or discharging. If something goes wrong, then safety alarm get activated. If everything is fine, then they are following the same thing. So these are of the three types where they have used different kind of models and different kind of surface temperature, thermal parameters. So it's a complete software based thing. So they use this as a electronics part into the battery management system of the battery, into the electric car, and then successfully they are using for long drive. And there are some efficiencies are there, and Tesla is really very smart in managing their battery management system, because the cell they are using, it's generating too much heat, but using a very smart management system, they are able to retain 85% of their state of health after the 3 lakhs kilometer of drive. Here I have some suggestions for those who are interested in reading more about the testing protocols. It's like some standard protocols were developed by the agencies, and in this Sandia National Lab has very good report about this, and I suggest everyone to read, either they are interested or not. This has lots of things about the battery system assembly, and then deciding all these parameters which I showed in previous slides. And then we have certain standard like SAE J2464, then UL 2580, UL 9540. These are the standard things which present time we are using for certifying the battery management system, which can be used in the electric vehicle. So if people are interested, they can go in these sections and they can find very interesting informations over there, and they can read there. So I just like to conclude my today's talk with this, that energy storage through the battery was in use from a long time in human civilization. As I showed you, from the last 2000 years back, we have a battery. And then battery is an environmental friendly, because don't pollute environment, and then energy efficient device, very energy efficient. And then to store the energy, it can be stored in the centralized and decentralized application both. Then battery is constantly evolving its technology, and because of this the price is going down. The chemistry of the battery is very important. As I showed, this has the lots of things to do with the state of charge, thermal runaway, and the gas evolution, fire, everything. So the battery chemistry is very important. And then several internal and external factors are responsible for accident if it has happened. And then in case of accident, consequences of the risk to the human life is very less if you compare with the other, and it can be minimized by choosing our chemistry very smart way and using a very smart battery management system. So battery management system and this pack and module design, basically it reduces the energy density of the battery, but it gives the benefit in operations. And battery has the play many pivotal role in the development of sustainable world, sustainable devices and drives, and this is the future of future transportation. So I like to thank you all guys for listening for today's talk, and I will be happy if you have some question. So I will be happy to answer those.
Thank you so much, sir. There are few questions in the chat box.
Yeah,
We
sure.
have a question from Harshita Luhani. She's asking which type of battery assembly is more preferable in electric vehicle battery and why?
Yeah, actually, as I told you, in the present time, because the cost matters a lot. So like Tesla, they are using NMC based, nickel manganese cobalt based batteries. Why they are using? Because it has very high potential, and they have the highest specific energy in all lithium-ion battery technologies. Other battery companies, they are going like Nissan Leaf, I saw they are using the old technology based on the iron phosphate. And some companies in the Israel, they are coming with the use of sulfur battery into the buses. So there are different companies, and they are using different technologies for these applications.
Okay, thank you. One more question is from Ms. Sangeeta. She is asking, is battery affected by surrounding temperature? The answer is yes, we have shown already. She's asking how to overcome this.
Yeah, it's a very nice question actually. Definitely, the lots of people in this talk has also introduced this thing, temperature factor. Like if you have some battery designed for the Norway, which is always below to 20 degree all over the year, and sometime it is going to the minus also in 15 or 18 degree. So if you have a battery designed in this country and then you want to use into the deserts of the India where the temperature is going 50 degree, so how the battery will perform? So see, there are several things we are using into the batteries. First thing, we are changing the cell chemistry. We are using certain chemistry which is not very much affected by the temperature. And for example, the tin into the anode. If you use the graphite, so the graphite based battery, if you have in your camera and you are going into some snowy places and want to take a picture, your battery will fail. So in that batteries, Sony has used the tin. By using the tin, the same battery you can use at the low temperature. So this limitation can be minimized. So this is one example I have given through the cell chemistry you can minimize. Another minimization of the temperature impact is the insulation of the cell. Like I have shown you the battery about the battery pack and module. So there you can use the insulating material which isolates your cell system from external environment temperature. So that way you can save. So both mechanical and chemical way are there to manage this temperature fluctuations, and you can use in a smart way.
Thank you, sir. The next question is from Harshita again. She's asking
Yeah.
how do we ensure operation of battery at low and high temperatures considering the safety factors?
So can you repeat the question?
How do we ensure operation of battery at low and high temperature considering the safety factors? And that this already been, I think,
Safety
covered. If you
factor.
want to add something.
Yeah, actually, you see, if as I explained you, there are two problems are there in the battery safety. One, it stops working. Another, it start working very exhaustly, and then it do lots of irreversible reaction. So if it is stop working, we can manage it through the cell chemistry. If it is going to have working very exhaustively, then in present technology we are using the battery management system as I showed. What our battery management system is doing, basically the electronic part, it is measuring the temperature with the current and the potential of the cell. So what it is doing, basically the heat generated is mostly coming from the polarization of the cell. So what they are doing when they are measuring, okay, the temperature is going high, then they are just stopping the cell. They are not drawing any current, and there is no fluctuation into the voltage. So by that way, they are minimizing the risk of accident.
Okay, thank you, sir. The next question, that which of the battery system is to be used for high efficiency? Which type of battery systems is to be used having high efficiency for having high efficiency?
As the efficiency is concerned, basically this NMC based system are very efficient if you are not using the graphite based anode, because present time battery technologies, most of the batteries efficiency is getting compromised by the graphite anode, especially when you are doing the high charge applications. So like I have shown in we are still in the generation 2, and when we'll go to the generation 3 where we have the NMC based system, high performance NMC based system. So cathode side we have a very minimal problem of the oxygen release from the cathode, but if we can modify some anode, definitely we will have this best battery system. And I can suggest over here the NMC with the graphite and then silicon will be a best energy efficient battery for drive applications.
Thank you, sir. The next question is from Mr. Ravi Kumar. He's asking, what is the battery pickup compared to vehicle speed?
Yeah, actually, see about this one, when we are using, again, it's a question coming from the battery management side. So what we are doing in the electric drive, basically, we are not only using the batteries, we are assembling this with the capacitors, basically, because capacitors are very efficient in giving the energy in the fast rate. Lithium-ion batteries are very good in storing large amount of energy, but when you start draining, they are not very smart. So for that one, we are using some super capacitors, ultra capacitors in between the system, and then battery management system used to drain energy first from the supercapacitor, and then this kind of management is going on to make a good kind of pickup into the vehicle.
Okay, thank you, sir. The next question is how to prevent thermal runaway?
Yeah, I think I have explained in my previous answer also, but again, so thermal runaway is a very important part in the battery management system. And then thing is to, if you want to minimize the thermal runaway, so first thing you have to do, you have to select your chemistry very well so that it generate very less heat inside the cell. Then second option, what you have to do, you have to use the cell packing material, not the module packing. Cell packing material should be very much thermal conductive, so that the whatever heat generated inside the cell, it should come out. And then you have to use very good cooling system, either it is the air circular or the liquid circle, and then it should withdraw that heat out of the cell. And third is from the electronic side. If the sensors are giving signal that the temperature is going high, then the operational temperature where the battery can sustain, generally it's a 60 degree, not only 60 or even the 45 is giving best. If you're going above to the 45, I have observation this is giving very bad performance. So if it is going above to that, definitely that particular cell or that particular pack or module must be stopped. So this is controlled electronically inside the cell. So these are the steps people are doing for for getting the good thermal management into the cell.
Okay, thank you, sir. Next question is very interesting. Prashant is asking why today's mobiles comes with non-removable batteries.
Yeah, actually, this is there is a two aspects for that. Because these companies basically they are thinking for one thing, if about the devices, if your battery goes out, you have to buy a new mobile. So most of the batteries they are using into the system. Now, I'm not considering the Apple phone, they have life of 4 to 5 years, but most of the batteries, if you see, is ending in 2 years, maximum 2 years. So maximum 2 years means you are going around 700 cycles of charge and discharge. So in 700 cycle, you are just losing your battery. So you have to buy a new mobile. So company is getting the business. This is the first. Second thing is coming from the battery management part. As I have given example of the Lenovo laptop in my presentation. So what mistake they have done? They have used the three cell battery pack into the laptop. And what is happening with this one? As I showed you in my note section, if you care over there. So when this lithium intercalation and deintercalation is going on, cell used to expand. That's called the breathing of the cell. So one cell is fabricated, it has some specific volume, but when you use it, it will swell little bit. So if your electronic board design is not good and you have not given a proper space to expand, so definitely what will happen? It will expand and then it will deform the cell and it may explode also. So because of this reason, this is second reason. And third reason is for this not allowing you to remove the batteries is this electrical corrosion problem. Because this electronic terminals, although we are using the gold coating on the connectors, but the chances of corrosion with the moisture is always there. So what they are doing packing so that you should not have any electrical loose connections, so that internal parts should not get damaged. So these are three reasons, but first reason is most important, the economy.
Okay. Thank you, sir. There are few more questions if you want to ask, if you are
Yes,
not
sure.
running. Okay. Mr. Srinivas is having three questions.
Yes,
First,
sure.
he is asking about the battery rating of EVs and EV voltage, ampere hour rating, kVh rating, etc.
Hmm. So, if you see this ratings of the battery, these are basically I have showed in I think in second slide where I mentioned about the specific energy. Why these ratings are there? There's the first question, because we want to know how much current and energy we can draw at what potential. So like we have certain devices which work at a particular potentials. So generally, if you see any battery, they are mentioning the voltage. This works at this voltage, and then this has this much capacity. So this is very important, because when you multiply the thermodynamic, means the energy stored in a battery is you can calculate from the Faraday law, and with that law you can multiply the cell voltage, and then you can get the ratings of the battery in ampere hour, and then that rating you can use for your technical purpose where you are going to use your battery. So I think these are the things for these ratings on the battery.
And
Second question.
that's the last question. In grid to EV charging system, what should be the charging and discharging current rating?
Ah. Okay, so this is basically coming from battery management side. So this depends on the kind of chemistry which you are using to the cell. And as I showed you in the battery management slide, it is decided by the company what kind of chemistry they have used, and then that chemistry what maximum current it can take. It's not like that you can use 16 ampere, then 32 ampere, it will go very fast charging. Yes, it can go, but there is a limitation from the material side. Material will not accept your extra current. So it's always coming through the modeling actually. They are doing different kind of charging and discharging, like constant current charging, constant voltage charging, or mixing up the both constant current and constant voltage. So it depends particularly on the chemistry which you are using. So I can't exactly say, okay, this is the best one, because this depends on the type of cell and application.
Thank you so much, sir. Thank you for answering all the questions very nicely. I just want to conclude that you have already shown us the right from the very beginning battery evolution and future suitability for electric vehicles, and then you have told us the battery working and battery generation, manufacturing, assembly, types of cells, fast charging, and its relation with the battery capacities, failure of battery and their consequences, and battery management system. And the last one you have shown us the report to be studied. If I think the participant who is working in the field of EVs would definitely be get benefited. I would like, sir, to have your PPTs also so that we can share them with the participant, whoever is interested. So thank you for the wonderful session again, sir. Your every session is being very appreciated by participants, all the participants. We have getting very good comments about your appreciated
Yeah,
lecture. And this is the certificate we want to show you in the form of our gratitude from the Sage family, from the EX
yeah,
department. So this is the certificate. Thank you once again, sir, for being here with us and always be available and so humble to accept our request. Thank you so much.
yeah. So I also like to thank to the SAGE group and sir to organize this kind of talk so that I can interact with the Indian diaspora. And I'm very happy that I can share my knowledge, and you have given me this chance. I'm very thankful to you and your group, and thanks to all audience who ask question, because it always sparkle the brain to think, and I'm considering this is a very important part of logical thinking, and I really appreciate the questions I got from the audience. Very thanks to the audience too, and your organization.
Thank you so much.
Good.
Thank you so much, all the participants. We will be connecting at 3 again.